Hi everyone, welcome to Seismic Data Processing course. In today's lecture we talk about the seismic resolution. We have two types of seismic resolution. One is called vertical, or also called the temporal resolution. So this vertical is used to detect the thin layers, the bed, that lies on the top of each other. So if you have one thick layer and another one thick layer, and between these two thick layers you have very thin layers, so we can use the vertical resolution to detect this thin layer. The vertical resolution is controlled by the frequency. So the higher frequency, the better resolution, because high frequency can detect the thin layers. But the problem with high frequency, it will be highly absorbed by the rock particles, so it will not be transferred for the deeper in depth. So the limitation, the minimum resolvable layer thickness. This is the minimum resolvable layer thickness that we can detect. So the minimum resolution, it is lambda divided by 4. So the wavelength divided by 4 is the minimum resolution that we can see on the seismic trace. So in the case of full wavelength, we have 1, 2, 3 layers. So the layer in the middle, the first one is full wavelength. If you see one complete wavelength, so full wavelength separated, the separate reflections clearly resolve. This is a clearly resolve. Clearly resolve, that means we can easily detect and see the reflectors within this layer. And we have half wavelength. So half wavelength, this layer is called resolved layer, also is resolved layer, but this is only just half wavelength, still separated but close reflections. You can see it's separated but very close reflections. This is one reflection, two reflections. So, and we can resolve, so we can see and detect this layer on the seismic trace. But if we have a quarter wavelength, we can see the reflector is changing from, we have two reflectors into one single reflector. So if a quarter wavelength, we have n resolved layer. Unresolved layer, reflections overlap. So the reflection will be overlaps. You have one single reflections. Detected only. You can only just detect it. And if we have single refraction, so in this case we have no layer, reflections merged between the upper thick layer and the lower thick layers. So the thin layer, we cannot detect this layer. No, not visible. Not visible because the lambda in here is 1 to 4 lambda, is less than 1 to 4. So if the lambda is less than 1 to 4 lambda, that means this is very thin. We cannot detect this layer within the vertical resolution. So you can layer thickness depend on the lambda. If you have the wavelength is bigger than a lambda, so full wavelength, half wavelength, this is half of the lambda, quarter 1 to 4 lambda. But if it's less than 1 to 4 lambda, we cannot detect the thin layer. You will have overlapped reflections between for both the upper and lower layers. We have two factors that control the vertical resolution: the frequency and 1 to 4 of the wavelength. If we have low frequency, that means we have very long lambda, the wavelength will be very long, and this is very useful for the deeper exploration, for deeper depth. High frequency, we use the high frequency, that means we have very short lambda, the wavelength will be very short, and this is very useful for the shallower depth and to detect the thin beds. So if you have very thick layers and very thick layers, and between them we have very thin layers like a sandwich, So on the seismic trace, if you have low frequency, within the low frequency you will see it's hard to detect the thin layers, low resolution, thin layers not resolved. But if you use the high frequency, you can see you have high resolution, thin layers is resolved. So we resolve, that means we can see and detect the reflections of the seismic wave. The other type is called the horizontal or lateral resolution. So it's the ability to distinguish between features side by side, not one above each other. In this case, it's side by side. For example, if we have two faults or edges of beds. We have two main factors that control the lateral resolution. The one is a frequency. We have another factor is called imaging aperture. This one for range of reflections, analog records. So imaging aperture, when we send the seismic wave, when the seismic wave hits the reflectors, the surface where the wave is interfere, and when it's back to the surface where the receiver is on the surface. So we have like bunches of reflections, not one single point, we have multiple of reflections. And these reflectors, they have angles, so the collection of all these reflections called imaging aperture. So these are the two factors. So if you have very large imaging aperture, they can capture all the thin beds. So we have two cases. So this is the unmigrated data and migrated data. This one is still not clean, is not representing the true geological subsurface geological layers. It came from different angles, but the software, but the receivers did not understand that. It will consider it's coming from directly from the areas below the receiver. But migrated data, we have to use the computer processing to tell the computer to back all these paths to their original. So we know all these paths came from this angle, if we have a dipping or not. Unmigrated data use the Fresnel zone. This Fresnel zone is the area below the refractors, where it will reflect all the reflectors as a bunch of data. And in migrated data, we use the Rayleigh criteria to determine the resolution. As we said before, when we send the seismic wave, it will not back as individual, it will back as a bunch of reflectors. Okay, and this is the area where all the reflectors back as a bunch of data is called the Fresnel zone. Why it's important lateral resolution? So as we said, lateral resolution, how close two side-by-side reflectors can be before they blur together. Have two reflectors before it's a blur, that means before it's overlap. So for example, if the Fresnel zone covered 100 meter laterally, then feature smaller than 100 meters will not be individually resolved. So that's why we use the Fresnel zone size to determine the limit of the lateral resolution in seismic data. So in this illustration, we can show the reflections come from zone rather than points because of the curvature. So it's coming from a zone rather than one individual point, and because of the curvature, and we can calculate the radius of this curvature from the velocity divided by 2 and time divided by frequency. So depending on the size of this curvature, it will determine the resolution. Okay, so the Rayleigh criteria. We use the Rayleigh criteria, as we said, to convert the data from unmigrated data to the migrated data. So two features can be distinguished if they are separated by at least half a wavelength. So two features can be separated if they have lambda divided by 2. And you know the wavelength is velocity divided by frequency. So the higher frequency, the small lambda, the good resolution, and low frequency, large lambda, poor resolution. So the factor that controls the horizontal resolution is something called the CDP, common depth point. The common depth point is the middle point between the source and the receiver. If this one the source and this one the receiver, so if you use large sensor spacing, object cannot be delineated. If you set the receiver and the distance is far away, so you cannot catch the small lenses in the middle. But if you use a lot of source and receiver, so small sensor spacing, object clearly delineated. Multiple source and receiver objects. If you use multiple source and receiver, we can catch all the lateral changes, all the lateral features. So the key in here with lateral resolution, we have to use multiple sources and receiver to catch the small changes. So as we said, we have two types of resolution: vertical resolution, lateral resolution. The vertical resolution is controlled by the wavelength, and the wavelength is the velocity divided by the frequency. What is that vertical resolution meaning? Can we separate two reflectors, one above the other? How can we do that? So the vertical resolution is lambda divided by 4. This is the lowest resolution. Anything below the lambda divided by 4, we cannot see this thin bed. Lateral resolution, we use Fresnel zone diameter. Can we separate two reflectors side by side? We can do that if we have the lateral resolution equal to 2, the radius multiplied by frequency, that equal to velocity time multiplied by frequency. So this is all you need to know about the vertical and lateral resolution. Thank you for watching, and see you in the next video.